Okay. So here so after we count the number of when the floating point of it, the flop means it can be either addition or multiplication. Okay, so the addition subtraction are counted as addition operations, and the multiplication and division are counted as multiplications. Okay, so I think in modern days, flop means either an addition or a multiplication. Okay, but if you read books 20 years ago in computation, then one flop means one addition plus one multiplication. That's the old definition of flop. Okay, but nowadays we use the flop. Okay, it can be now we use the modern definition. Okay, then okay, after we can prove that when we do when we compute when we factorize the A matrix, okay, that means we compute the LU factors, then we need n cubed over 3 multiplication plus a lower order term, okay, and we need n squared over 3 plus a lower order term. This is not exactly n cubed over 3. It's n cubed over 3 plus second order term, which is in the terms of n squared and n plus a constant. But when we consider the cost, usually when we consider the cost for a large value of n, right, there's no point to consider the cost of computing for small n, because it's fast anyway. Okay, and then this is what we want to consider. Then by solving the AX equal B, okay, by substitution, by forward substitution and backward substitution, then we need n square additions and n square multiplication. And you can see that now for a large value of n, then most of the cost, okay, most of the time is spent in factorize the A matrix, right? Because n cubed is grow faster than n squared for large value of n, right? So let me mention this a little bit, okay? When we and from this, so it comes to stop sharing, ใช่ไหม ขึ้นก็ขึ้นแบบนี้มาขึ้นมาอีก
ใช่เพราะว่าเป็นคนเข้ามาในกลุ่ม
เราไม่ต้องโชว์ไม่ได้ เราไม่ต้องโชว์ไม่ได้ตรงนี้มันจะขึ้นมาบนจอก่อน
พี่เพิ่มมทำม3 จุดมีเอาแกลเลอรี่ออก
ไม่ได้
ไม่เป็นไรค่ะก็มีคนเรียนเอาไม่ได้
So okay, now with okay, when we solve the linear equations, okay, usually if we solve ax equal b only once, then the LU factorization has no advantage over the usual Gaussian elimination process. But you will find that in some applications, in some applications there are we solve AX equations many times for a fixed A matrix and with many the B vectors. If we so in this situation, you can say that when we use the Gaussian elimination, okay, if we apply the row operations to A augmented B, okay, until this one is in echelon form. So if we change the B matrix, okay, then we have to do the elimination process again. So we have to apply the row operations again. So we apply the row operations again, and that process you can see that it's the number of flops is n cubed over, okay, in the order of n cubed or n cubed. So, but if we have to solve this equation for many vector b's, we have to do each time we change the b vector, we have to redo the row operations. Okay, this is obvious. Now, if we have to solve this for by using the LU factorization, you can see that when we do this, the A matrix, once the A matrix is factorized, so we store the LU. So whatever vector, so the LU factors does not, okay, the LU factors do not depend on the vector B, right? Of course. Then when we for each B that we change, we don't have to refactorize this. But what we do is we only do the substitution, which is in the order of, when we do this Gaussian elimination, okay. The flux release is in the order of O n cubed. But then if we do this, when we solve the LU factorization, the factorized LU factors is O n cubed, and we do this only once. Okay, after that, for each B, then we know that the substitutions then is order of O n squared. So if we have to solve this equation Ax equal b for many vector b's, if we use the LU factorization, okay, we only do the LU factors once, and then after that, then we do the substitution, and then the flux required is only in the order of O n squared, which is much less than if we have to do the Gaussian elimination every time for the vector, for each vector b. Okay, so far we only talk about the normal procedure of Gaussian elimination or the LU factorization. But now we consider a different system. Here, in the first equation, the coefficient A11 is 0. Now when A11 is 0, then you can see that we cannot do the normal Gaussian elimination, right? Because when we use this, when the A11 is 0, then we have to use A11 to divide the equation, right? And then so when we divide something with 0, then the computation process terminates on computers, right? And so we cannot do that. So what we do is that we have to, but we know that by row interchange, then the solution doesn't, okay? Then we obtain a different system, but with the same solutions, the same set of solutions. So by doing that, so okay, so what we do is we do the row interchange. We swap, we replace, okay, we swap between equation 1 and 2 or 1 and 3. Okay, either of them, either pair will do the job. But now, okay, that's one reason. But another reason is when we do this. But normally, if we don't have the 0 here, we also in practice we also do the row interchange. Okay, and this process is known as partial pivoting. Why we do this? Now, okay, look at the same example. This example again. When the 0 becomes a very small number. Okay, when we do the Gaussian elimination, we have to divide this one. We have to just this number. Okay, we have to divide this equation by this number, right? To normalize this to 1. Okay. In computers, we can, okay, the numbers that we store, you have to understand that all the numbers we store in computers are not exact numbers. Why? Because I think we normally in we use the numbers, okay, real numbers on decimal base. But in computers, it's binary base. It's binary digits. So that means, let's say, for example, 1 or 2, you see that this is exactly number 1 and 2. But then when we convert this into the binary form to store in computers, then 1 and 2, okay, cannot be stored exactly on computers. Okay, no matter how many digits, how many binary digits we use. Excuse me. Okay. So we have to truncate. So all the numbers stored on computers have is not the exact number. They have some small error. Now you see that if we divide this, okay, if we divide the equation 1 to normalize the equation 1, then you see that when we divide by this number A11, what happens? All the errors are amplified because when A11 is very small, 1 over A11 is a very large number. Then in doing this, we are amplifying or magnifying the errors to a great deal extent, or to a great extent. Okay, and then that error may creep into the process, and therefore the solution may not be accurate. To reduce the effect of this, okay, so we choose when we do the equation, okay, we do this, okay, we do the row interchange so that the diagonal element we are dealing with each time at the largest magnitude. At the largest magnitude. Okay? At the largest magnitude. And that's the idea of the partial pivoting. Okay. And the details, if you want more details on this, you can read books on the numerical computation. Okay, but this is the details of this is also in another course, which is a 507 computational techniques. Okay, and okay, that's the. And when we do the partial pivoting, okay, just to end this review, when we do the partial pivoting, okay, then the Gaussian elimination process is equivalent to factorize A as the PLU instead of A equals LU. P is what we call permutation matrix. Okay, P is a permutation matrix. What is permutation matrix? Permutation matrix is that permutation matrix is the identity matrix. Okay, that has been applied. That to which the row interchange applies. So we apply the row interchange to the identity matrix, and then we obtain a permutation matrix. Okay, and the permutation matrix will reflect the row interchange. All the information that all the information on row interchange will be stored in the P matrix. Okay, and because of that, but normally we don't store the P matrix as a whole matrix, because you see that a permutation matrix has one element which is non-zero, and that is equal to 1, and the others on that row are 0. And then to store the permutation matrix, we use only a vector. Okay, we use an integer vector to store the permutation matrix in computers. Okay. So that's the end of the review. So and we will move on to the another review. Okay, after this.